How about no? Okay. So, yesterday we really focused our attention on calculating equivalent resistance, currents in a potential difference across resistors and series circuitry. Today, we begin our discussion on those same concepts, but in parallel. Now, for some reason, this chapter's slides are incredibly messed up, okay? Today's discussion even has even more slides that are messed up that I can't even fix. So, I'll have to talk you through it, okay? So, again, yesterday we talked about series circuit requires all elements to conduct electricity. There's no alternate pathways or anything like that. As seen below, this is the wrong image, okay? I'm going to go to the next image. We have a burned out filament in a string of bulbs. It has the same effect as an open switch. I'll go here. As you see here, this burned out bulb, basically like open, it's like having an open circuit. Electricity is not going to flow. And since it's not going to flow beyond this, since there's no complete loop from its EMF source, these bulbs will also not light. Okay? Now, parallel arrangement describes two or more components of a circuit that provides separate conducting paths for current because the components are connected across common points or junctions. And lights wired in parallel have more than one path of current. Parallel circuits do not require all elements to conduct. So that's this one. So when you begin diagramming your schematics and actually creating these in class with actual devices, hopefully, you see here, if you think about it as this, they're kind of being like one main pathway with some alternate pathways kind of offshooting to the source. Okay, there's a couple different ways where when you start wiring parallel circuits that you can go about that. Okay, but think about this when doing this. If you can minimize the amount of material that is used in the long run, especially when you're talking about, say, rewiring a school or wiring a school in the first place. Okay, minimize materials required, minimize costs. So you could do it expensively or not expensively. But again, anytime filament burns out, let's say this filament burns out here, well, guess what? The electricity can still continue to flow that way and still connect those down the line. All right, so the image right here is kind of very similar to what you're going to be doing. All right, you see here, we got our EMF, our battery. Got clips to go to these two common points, and they continue to go like that. Okay, where electricity could go through here. Okay, but if that burns out, it just bypasses it and continues on going that way. Now, when we calculate equivalent resistance, resistors in parallel have the same potential differences across them. Asterisk. Resistors in parallel have the same potential differences across them. We just go. Oh, that was good. Yeah. We'll wake up. I just haven't had enough coffee this morning. The sum of currents in parallel resistors equals the total current. So those two statements right there are going to be utilized when we do our breakdown of resistors in complex circuits. This time, however, whenever we calculate the equivalent resistance in parallel, it can be calculated using a reciprocal relationship. Okay, so I'll be honest. There's one way that I calculate it, you might have shorter ways. Okay, that's just the way that I've become accustomed to doing it when we do this, and so that's kind of where I stick with. Again, it's math. A lot of times there are other pathways, much like parallel circuitry, that you can get to an answer. Okay, if you know a shorter method, use it. But I'm going to show you my way, and then you can take it where you want. Okay. So we're going to have a very similar setup that we did, or we had yesterday, with the exception that all of these resistors present are going to be in parallel. Again, we have another 9-volt battery. We've got 4 resistors, 4 light bulbs. Let me get this here. There we go. So, we have a 9-volt battery connected to 4 resistors in parallel. Find the equivalent resistance for the circuit and the total current in the circuit. So what do we know? Well, we know that we've got a 9-volt battery, we've got a 2 ohm resistor, 4 ohm, 5 ohm, and 7 ohm resistors. You find the equivalent resistance and the current. Okay. Schematic diagram of that setup is right here. So first we need to calculate the equivalent resistance because we need that to calculate current using that same formula from yesterday. And then this is where it gets all kind of messed up. So again, you're going to rearrange that equation right there for potential difference, rearrange it for I, and then you get this lovely little jumbled mess right here. Okay, so I'm going to kind of rewrite this a little bit. And what do I want to do? Okay. So kind of how I go about it is going to take all of your resistors and place them in reciprocal fashion. Let's see, was it? It was 2, 4, 5, and 7. 2 ohm plus 4 ohm plus 5 ohm plus 7 ohm. So what we want to do before we really do anything is we want to treat these kind of like small little individual fractions that we want to convert into decimal. Okay, so we're going to take 1 over 2. What's that decimal? 0.5. 0.5 over 1 ohm. What is 1/4 decimal? Very good. Okay. What is 1/5? You're so good. And lastly, 1/7. 0.14 over 1 ohm. Next, what we're going to want to do is now add up those decimal values. What do we get? 1.09 over 1 ohm. We're going to take that answer, take the reciprocal of that, so it's going to be 1 ohm over 1.09. What do you get? 0.917 ohms. That's kind of again, if you know a quicker method, by all means, for this kind of stuff, I just really like to show step by step and the slow process. Okay. Start off by placing them in, yes. Oh, because you're turning these into decimal forms, really, to add them up. Okay, so the over 1 ohm. It's basically like it's just to show the reciprocal relationship, really, and that's the extent of it. Okay, to do it correctly mathematically. Because if you were to add these up like this and then try to do it, it doesn't work. So you have to convert these fractions into decimal points because this ohm stays on the bottom. Okay? And then to get ohm on top, take the reciprocal. Okay? So again, start off in fraction form, convert each fraction into a decimal over ohm, take the reciprocal, and divide it to get your equivalent resistance. Let's do a couple more. Open up your textbooks to page 655. $655. Let's look at number 3. Oh, one thing we didn't do in the practice is find the current, but we're going to do that in this practice problem. So that slide in your notes isn't messed up. We'll revisit that here in a second. But number 3 says a 4.0 ohm resistor, an 8.0 ohm resistor, and a 12.0 ohm resistor are connected in parallel across a 24-volt battery. A, what is the equivalent resistance? What is the current in each resistor? So, do we know what our potential difference is? 24 volts. One resistor is 4 ohm. Our second resistor is 8 ohm. And our third resistor is 12.0 ohm. So to find the equivalent resistance again, 1 over REQ, we got 1 over 4 plus 1 over 8 ohm plus 1 over 12 ohm. My ohms are starting to look like R's. So we get what we said is 0.25 for 1/4. What about 1 over 8? 0.125 over 1 ohm. What about 12? 0.083, repeating, for 1 ohm. And so when you add those up, what do you get over 1 ohm? You get 0.45. Yes. Over 1 ohm. Take the reciprocal. You get 1 ohm over 0.45. So what is the equivalent resistance? 2.18, or we'll go 2.2 ohms. Okay. Next thing we have to do is determine the current. Okay. So we have to do it, I believe it says, in each resistor. So we have to do this 3 times. Okay. So for the current in the first resistor, I call I1. We get delta V over R1, which is 24 volts divided by, what was that? 4, thank you. 4 ohms. We get 6 amps. Do the next for the next resistor. Again, 24 volts divided by 8 ohm. 3 amps, that's an A. Dorfler. And the third, 24 volts over 12, we're going to get 2 amps. I want to do one more. Okay, I want to do number 5. Oh, what did I do? I want to do number 5. Number 5 says an 18 ohm, a 9 ohm, and a 6 ohm resistor are connected in parallel to an EMF source. A current of 4 amps is in the 9.00 ohm resistor. Calculate the equivalent resistance of the circuit. And next will be what is the potential difference across the source. So we'll come back to that. So again, our EMF, we don't know. Our voltage, we don't know. We're going to solve for that. We know what our current is, though, in the second resistor, and that's 4.0 amps. And so our first resistor, 18 ohm. Second resistor, 9 ohm. And third, 6 ohm. So go ahead. I want you to calculate the equivalent resistance of this circuitry. I hope I'm recording this. Okay, good. What do we get for the equivalent resistance? Do we have that yet? If not, I still see people working, so we're gonna hold off for a minute. You in the front corner here. 3 ohm. Okay, very good. The next thing for part B says, what is the potential difference across the this particular resistor? Or across this source, okay? So this time we're not going to rearrange that equation. We're just going to simply do delta V is equal to I2 times R2. Okay? And so, because we know which one to use because of the problem. It says a current of 4 amps is in the 9 ohm resistor. So that's why we're using the value for the second resistor. So we got 4 amps for the current. We've got 9 ohms for the resistance. So what is our potential difference? 36 volts. And then from there on out, if we wanted to, which I think you've got a handle on now, we could determine the current in the other 2 remaining resistors if we wanted to do so. But that's that. I don't think there's any other ones I want to practice here. Nope. Any questions? All right. For your homework, which I have to go get off the copier, you need to do 1 through 10 again. And looking at number 1, number 1 is a challenge question. I want you to think about it. Okay? But everything else should be pretty straightforward as far as I can tell. So those of you at home, you should have this ready and available to you on Classroom. The rest of you want to go get your hard copy. Well, apparently I'm having trouble too, but we gotta stop that. We can't let that happen. All right.